Welcome to the Explainer. So, have you ever wondered why that trusty kitchen gadget you bought 20 years ago is still going strong, while a brand new smartphone cable literally frays and fails after, a month? It's wild, right? Well, today we're decoding the invisible math of manufacturing quality. We're going to look at the exact science, the philosophies, and the rigorous testing that dictate why some products just last a lifetime, while others break almost instantly. Let's get right into it.
To really understand how this works, we actually need to rewind to a massive, real-world mystery from the mid-1980s. It involved the Sony Corporation. So at the time, identical Sony TVs were being built in two totally different facilities. One was in San Diego, California, and the other was over in Japan. Now, they were built from the exact same design specs. There were literally no special markings to tell them apart. And yet, the Japanese-made TVs were flying off the shelves way faster than the US-made ones. Customers were actively hunting them down, saying the color was sharper and the hues were just more brilliant. But how could that be if they were identically designed?
Well, when investigators finally dug into the factory data, they found two completely different philosophies at play. See, the San Diego plant was incredibly proud of their zero defects record. Every single TV they built fell safely inside the acceptable design limits, but the measurements were just spread evenly across that whole acceptable range. The Japanese plant, though, they had a totally different approach. They actually produced a few technical defects that had to be scrapped, but the vast majority of their TVs were clustered incredibly tightly right around the absolute perfect design target for color density.
Now, what's really interesting about this slide is how the Taguchi loss function translates that philosophical difference into cold, hard cash. It was developed by a brilliant statistician named Genichi Taguchi, and he mathematically proved that any deviation from the optimal target costs society money. We're talking customer dissatisfaction, field repairs, lost brand reputation, the whole shebang. That broad, good enough US approach on the right, it resulted in an average quality loss of $1.33 per unit. But that super tight, target-focused Japanese approach on the left was only costing 44 cents per unit. The market could literally see the difference, and the Japanese approach completely won out.
Section 1. The Philosophies of Quality. Shifting from defect detection to defect prevention.
So to pull off that monumental shift, going from just spotting a bad part at the end of the line to actually preventing defects in the first place, we have to look at Kaizen. It's a Japanese term that basically means continuous, never-ending improvement. In a Kaizen environment, quality isn't just some final inspection checkpoint before the product goes out the door. It's this relentless, daily pursuit of perfection baked right into the company culture. Everyone, from the CEO straight down to the line operators, is actively looking for ways to make the whole process just a tiny bit better every single day.
And that leads us right to this core philosophy. Quality must be built into a product and not merely considered after the product already has been made. Think about it. This means design engineers and manufacturing engineers have to be talking constantly from day one. You just can't design something that's impossibly difficult to assemble and cross your fingers that the factory floor will figure it out. The design itself absolutely has to guarantee quality.
Deming was huge in championing this holistic view, totally transforming wartime industry. With his revolutionary mandates, he demanded that we stop relying on mass inspection to catch mistakes. He really pushed management to break down those silos between departments and completely eliminate arbitrary numerical quotas that were just forcing workers to rush. Basically, he proved that a factory is a living, breathing system of people and machines, not just a blind assembly line.
Section 2. The Math of Manufacturing. Statistical Process Control and Mapping the Chaos.
So how do we actually control this living system using math? Well, in any factory, variation is the ultimate enemy. But here's the thing. Not all variation is the same. First up, we've got chance variations. Think of these as just the random background noise of life. Tiny little shifts we can't easily control. But then we have assignable variations. These are specific, traceable causes that we can actually hunt down and fix. Think along the lines of a cutting tool getting dull, a machine vibrating a bit too much, or maybe a bad batch of incoming steel. The entire goal of statistical control is to track down and eliminate those assignable variations.
To map out this variation, engineers rely on the Gaussian normal distribution curve. You probably know it as the good old bell curve. If a process is statistically stable, most of the product dimensions are going to cluster right around that average value in the dead center. The width of the curve shows you the dispersion, right? Basically, how far off the mark things are getting. Now, in standard, healthy manufacturing, the goal is to have 99.73% of all parts fall within 3 standard deviations of that center line.
But as you know, technology kept advancing, and honestly, 3 standard deviations just wasn't cutting it anymore. Just think about the millions of credit card transactions happening every day, or life-saving medical devices. You need something way stricter. That's why the industry evolved to 6 Sigma. Under 6 Sigma, the tolerance for error drops to an incredibly tiny number, 3.4. Yep, just 3.4. That is the absolute maximum number of defective parts allowed per 1 million parts produced. It is a staggering standard of near absolute perfection.
And this brilliantly illustrates how operators actually keep up that level of perfection on the factory floor. The Schuhart control chart. It tracks the average dimensions of sample parts over time. See that solid line right in the middle? That's the grand average, the perfect target. The dashed lines at the top and bottom are your upper and lower control limits. As long as the dots, which are real-world samples, are just bouncing around randomly between those limits, the process is completely healthy. The operators are literally watching the math unfold in real time.
But check out this specific moment on the chart. Notice how the dots are creeping steadily upward. They're moving in a very clear line straight toward that upper control limit. Now that's not random chance. That is a dangerous trend. In this specific case, it turned out to be a physical cutting tool that was slowly wearing down, making the parts just slightly larger over time. But here's the genius part. Before the parts actually crossed that line and became defective, the operator spotted the trend, stopped the machine, and changed the tool. That abstract math literally just saved the company from churning out a whole batch of useless, super expensive parts.
Section 3. Finding the hidden flaws. The high-tech world of non-destructive testing.
All right, so we've built a fantastic product using statistical math. But when it comes to highly critical components, like, say, aircraft jet engine turbines or a pacemaker going inside a human chest, how do we test them to absolutely guarantee they won't fail? And more importantly, how do we do it without breaking them in the process? Well, one surprisingly simple method is liquid penetrant inspection. We take a metal part, clean it up nice and dry, and cover it in this special fluorescent liquid. Through the natural magic of capillary action, that liquid seeps way down into microscopic surface cracks. I'm talking cracks as tiny as 0.1 micrometers wide. Then we just wash the surface clean, apply a chemical developer, and boom! Suddenly those invisible, potentially catastrophic surface cracks light up brilliantly under a blacklight.
Okay, let's dive into this next one, magnetic particle inspection. So what if the flaw is just barely underneath the surface, where a liquid penetrant can't even reach? Well, if the metal is ferromagnetic, engineers can apply a super strong magnetic field to it and dust it with really fine iron particles. If there's any hidden internal defect, it physically interrupts that magnetic field, which forces the magnetic lines up to the surface. It basically creates a tiny new magnet right above the invisible flaw. The iron dust instantly gathers right there, drawing a perfectly visible map of the subsurface danger zone for the inspector. It is so cool.
And the hunt for invisible flaws goes even deeper than that. Engineers use ultrasonic inspection, where they beam high-frequency sound waves straight into a part and measure the echoes bouncing off internal cracks. Then there's acoustic emission, which is literally listening, with these super-sensitive, specialized sensors for the tiny stress waves generated by a material crying out as it begins to crack under pressure. And of course, there's radiography. This uses X-rays to look straight through solid metal, easily spotting density differences and hidden air bubbles. It's just a massive, high-tech arsenal entirely dedicated to ensuring our safety.
Which brings us to the end of our explainer today. But I want to leave you with a thought. Take a second and just look at the device you're using to watch or listen to this right now. It is a wildly complex assembly of glass, metal, and microscopic circuits. Think about what invisible math, what rigorous Kaizen philosophies, and what intense non-destructive testing kept it from breaking in your hands today. The next time you use a product that just works perfectly, day in and day out, take a beat to appreciate the hidden world of quality assurance that actually made it possible. Thanks so much for learning with me today, and I'll catch you on the next one.